You've read the rules, you've created your strategies, you've put in the time, you've done the math. Now it's time to show us what you've got. Welcome to this week's episode of FMA Plus.
Welcome back for week 3. This week we've got Team 1640 Sabotage from Downingtown, Pennsylvania, Team 222 the Tigertrons from Tunkhannock, Pennsylvania. We've also got Team 708 Hatters Robotics from Horsham, Pennsylvania, and Team 1923 the Midnight Inventors from West Windsor and Plainsboro, New Jersey. So we're going to kick it right off with Team 1640 Sabotage. Let's take a look at their robot and their season, and of course, their famous swerve drive. We're here with Team 1640 Sabotage. I've got Jacob, Joey, Aaron, and mentor Sanjay here, and they're here to tell us a little bit about their team and their robot for the season. So Aaron, why don't you kick us off and introduce us to Team 1640?
We are Team 1640 Sabotage, a community team based out of the Exon Square Mall in Pennsylvania. We have a storefront in the mall called Downingtown Area Robotics. Our workshop contains our FLL Junior, FTC, FLL, and our FRC team. This year for the 2020 season, we are grateful to have gotten the opportunity to attend a Week 1 competition. I'm Aaron, and I'm the chairman's lead, one of 2 co-pick captains and a machinist.
I'm Jacob. I'm a co-lead programmer, the driver this year, and a co-team captain.
I'm Joey. I'm part of CAD design, and I'm also a co-captain as well.
Very cool. Yeah, I love the idea of working in a storefront. I know, Libby, you said you've had some experience there as well. It's very resourceful, and I imagine the exposure is great.
Exactly,
right?
It's a great way to meet people.
Yeah, people come in all the time.
Cool. All right, so let's dive into the robot. Jacob, why don't you run us through the requirements that you guys set for your robot for this year's competition?
Yeah, when looking at the competition this year, we started outlining our goals for the competition, not necessarily like mechanical goals, like how we would accomplish things, but what we would accomplish. So we wanted to protect our new swerve design this year because it has a lot of 3D printed parts. We wanted to move fast across the field. We didn't want many bottlenecks, and all of that led us to settle on a low bot that could fit under the trench and also make it across the rendezvous zone as needed. We also wanted the intake and the shooter on opposite sides of the robot so we could pick up on one side and shoot out the other without turning around. And we wanted a climber because we felt it was absolutely necessary in terms of scoring. And we needed to build within our capabilities, and we couldn't make too many advanced mechanisms that the team couldn't accomplish.
Sounds like you guys had a lofty set of goals for sure. That's awesome.
Absolutely. So let's walk through sort of your brainstorming within those requirements.
Yeah, so we started out by setting a timeline of when the game functions would be necessary. We knew that climbing was a huge part of the game, so having it early on would be necessary as opposed to last year where we didn't have it at our first event. We knew shooting would be useful, but the 3-point goal would probably only be useful late season, and a consistent 2-point goal with occasional 3-point would be key at beginning competitions. We felt a buddy climb wasn't essential to our game this year, so we didn't focus on one. And once again, we knew we didn't have the capabilities for making some more advanced mechanisms, so we moved away from like an arm diagonal concept that stored the balls and articulated around the robot and moved towards a U-turn concept kind of shaped like a reverse S to move the balls through our robot.
Nice. All right, so one of the big things that 1640 Sabotage is known for is the swerve module or the swerve drive approach. You guys have proven time and time again that you guys know what you're doing when it comes to that mechanism. So, Aaron, why don't you introduce us and maybe walk us through the CVT swerve?
Yeah, so from 2010 until 2019, our swerve was based upon one design, which we improved on each year. During the 2019 off-season, we spent a large portion of time redesigning our CVT swerve. Our new design is way more compact than our previous design. And with the new design, we get optimal power at all times with our CVT. And this is now placed inside the swerve instead of on top, as before we've done in previous years. We had time to test our swerve, but we still had doubts because this year we're using so many 3D printed parts. And at the competition we attended, Hatboro, we saw that our 3D printed parts worked, and we were really happy that that worked. But we still saw that we had other failure points, which we are very happy we got the opportunity to fix and figure out. So that was really nice to see.
So obviously building on a really strong foundation, quite literally, for the robot with your drivetrain. Joey, let's talk about sort of the intake and the funnel mechanisms on your robot.
Yeah, so our intake uses a bar of mechanism rollers that extends outside the frame perimeter. An issue we had at the beginning of the season was that once the balls were intake, they would run up against the frame and have like a vertical velocity and just hop out the robot. So our solution was to put some rollers that basically went on top of the intake, try to deflect it towards the inside of the robot. So one of the bigger problems that we had to overcome this season was manipulating the balls in a way that they would go in one at a time rather than two going in at once and jamming the entire mechanism. So our funnel system basically has two belts that run on either side of the ball, and there's on the bottom of the funnel system. There's two different size wheels, basically creating two different speeds on either side of the funnel, so that one side will always have a higher speed, so it will go in before the other side will.
Jacob, we've heard about how you pick up balls off the floor and how you funnel them. I'm curious about your indexer and your shooting. Maybe you could talk a little bit about that.
Yeah, so like I said earlier, we went with a U-shaped indexer that helps us to maximize like the space efficiency throughout the robot and store the ball centrally in like one lane of the robot. We could store up to 5 balls this year, so the maximum you can hold at one time. And we use like belts to move the balls around. We doubled the belts up just in case they broke at one point in time, which was a pretty useful feature because we realized that it was hard to do maintenance on the indexer. The U-turn would help separate jams with a large diameter wheel that separated the balls as they went through. We also had sensors that helped separate the balls as they went through the indexer. So if they touched each other, they would jam, but they never actually touched each other during a match, which was pretty useful. When they got through the indexer, they made it to the shooter, which was powered by 2 motors and 1 servo-powered hood that could basically allow us to shoot from almost any spot on the field as long as our shooter power would allow for it. And we learned at Hatboro that the servo on the hood could fail sometimes, so we added a mechanical stop to automatically shoot from up next to the target that you saw at Hatboro a couple times. And we ended up improving the consistency of the hood with the 3D printed part and focused on consistency over 3-point accuracy.
Yeah, you mentioned something in here that says no wasted matches ever. What does that mean?
Yeah, so no wasted matches ever means that due to the backups that we had, like the mechanical stop in case the servo failed, most of our matches were never wasted. We were always able to shoot directly up next to the goal, and the robot was always able to perform the shooting function, which was one of the only scoring functions in the game besides maybe you could climb or something. So it was really essential that we had that backup plan and that none of our matches were wasted in that sense, and then we could also learn from our other failures throughout the matches.
So you mentioned climbing as another scoring opportunity. Aaron, what did 1640 do to tackle the climbing challenge this year?
So this year, our climber uses lead screws to move our hooks up and down, and this is useful as it makes our climber unback drivable, preventing our robot from ever falling down. Our climber consists of a shifting gearbox, which can drive the lead screws up and down. From this, we could change the gear ratio with more speed when our hooks are raising, and more torque to lift our robot after the hooks are placed on the bar. At the competition that we attended, we learned just how close we were climbing to the end of the match. Our robot was barely able to get off the ground in time, so to make climbing easier, we added larger pistons, which could fold the robot, and constant force springs, and this allowed the robot to retract after the time was up. In order to grab on the bar faster, we discussed a double hook, and this increases the possibilities of how we climb and decreases the chance of falling, as we did at Hatboro. And another thing we talked about is how one of our matches, one of our hooks broke, and to solve this, we began designing our double-sided hook to be thicker.
One thing I really like about that design is you hardly ever see shifting gearboxes used outside of the drive base. That's really the common application. I love the idea of having a quick mode to deploy and a slow, strong mode to hoist your cells in the air. That's very resourceful. Jacob, lots of moving parts on this robot, lots of cool functionality. Perhaps you could speak a little bit about the software that came with this robot.
Yeah, so we learned from last year that compartmentalizing a lot of our code was actually a bad thing at times, and that we learned to unify all of our scoring code into one kind of state machine. So we fixed that bad habit and started improving the reliability of our code and having less fail points throughout the matches. We also had to work on our first autons as a programming team. My co-lead programmer and I learned about autons like all throughout this year, but we didn't use them last year because they weren't necessary, and it was our first year programming the robot. So that was a big step up that we had to make this year. Then we also had to train new programmers so that there would never be a case where new programmers would be thrown onto the robot like what happened to us last year. And so we started training around 8 new programmers throughout the year in Java with our tank robot from 2016. We also added like driver automation features. So the operator, when they would try to use the elevator, it would auto shift based on if they're going up or down. And that removed a few buttons that they would have had to press throughout the match. We also added an automatic hood angle based on our distance from the target using the limelight. And we notably added an operator hood angle increment, which was a little constant that they could increment throughout the match that was multiplied by our automatic hood angle equation. So if it was a little high, they could make it a little bit lower. And if it was a little low, they could make it a little bit higher and settle on a good point at the end of the match where they could start like shooting like dead on into the goal.
Very cool. So I've got here in the notes that you guys want to talk about your use of carbon fiber. So Joey, why don't you walk us through that?
Yeah, so our robot has 2 carbon fiber shields on either side of the robot. And these serve as connection points for many systems, but also as the main connection point for the climber to the rest of the chassis. And they also protect the robot when we're climbing. And this is something that we laid out inside of our own workshop. So our design was to create something called a quasi-isotropic layout. Basically what that means is that the strength and rigidity of the carbon fiber is equal in any direction of force, especially since the climber is diagonal from the rest of the chassis. This is important. And the way we did this was to create multiple layers of carbon fiber with threading in perpendicular orientations. So this saves us a lot of weight over like aluminum, but it also gives us the same strength that we would have using traditional materials.
That's awesome. You guys not only understand the science behind why carbon fiber is so strong, but also how to make it. That's very, very, very resourceful. I think that's a great skill set to have too. Being able to make lightweight build materials from scratch like that is super helpful. Speaking of weight, last section here for Joey, it looks like you want to talk about the weight of the robot. So how did the carbon fiber play into that, and what kind of weight challenges did you guys come up against?
Yeah, so this season we took a pretty hard emphasis on cutting weight wherever it was possible. Even from like the beginning of the season, like prototyping, we've always been trying to be conscious of the materials and the heavy materials that we use in our prototypes. For example, like the chassis, we replaced a lot of those materials with lighter materials, cutting the weight down from 13 pounds to 4 pounds. So building with this weight really paid off in the season, since we were able to have a robot weight of 112 pounds. And that gives us a lot of room to improve the robot. For instance, like the climber that was previously mentioned, without making too many other sacrifices on other parts of the robot.
I love that. I like the idea. I don't think most teams think about robot weight conservation until it's too late. So I love that you guys are going through the design process and talking about what it's going to weigh at the end of the season there. What a cool look 1640 into your robot and your design process. Thank you so much for sharing. Are there any other stories you want to share with us tonight on FMA Plus?
Yeah, we also wanted to tell about how we've been hosting other teams at our workshop, and we actually have been working with other teams previously, and this has allowed us to really develop on our robot. And even after Hatboro, that really helped us to see how other teams had designed stuff, and we got to work together to fix some issues that we both faced. And we plan to also host a Mall Madness once we're allowed to go back to our workshop, and have a whole bunch of teams at our mall workshop, and we can all work together and have some fun competitions too.
I have a feeling people are going to be lining up for that when the doors finally open. So Sabotage, thank you so much for joining us tonight on FMA Plus. If I want to learn more about your team, where can I find you online?
So you can find our Instagram and Twitter at FRC1640. our website, team1640.com, which is a full wiki that details pretty much our whole build process and everything we did throughout the season. And one last note, I'd like to thank our mentors and parents for helping us throughout the season. Couldn't have done it without you guys, and we appreciate you all.
All right. Well, Team 1640.
Oh
my
my
lordy.
That was kind of dysfunctional.
Oh, that's
you know what?
perfect.
For the digital
Absolutely
era,
perfect.
it works just fine. 1640, thank you so much for joining us tonight, Jacob, Joey, Aaron, and mentor Sanjay. Appreciate your time tonight, and we will see you soon. Thank you so much.
Thank you.
I'll assume my
Thank you.
fedora's in the mail.
We'll be sending it soon with the vest.
Perfect.
Thank you, Sabotage. Appreciate a deep dive on the robot and the season. Jeff, who's up next?
Next up on our show, we have Team 222, the Tigertrons out of Tunkhannock, Pennsylvania.
We're here with Team 222, the Tigertrons. I've got Marina, Brittany, and David, as well as mentor Cliff, to talk about their team and their robot this year. So, Brittany, let's kick it off and tell me a little bit about your team.
We are Team 222 Tigertrons, and we have a young team starting out this year. We have been the Tigertrons since 1999, and we're part of the Littles since 1997. We have roughly 22 kids this year and also have 8 mentors this year. They have helped us through life skills throughout the years.
Awesome. Yeah, I'm a huge fan of the Tigertrons. I love the branding. I love the imagery. And obviously you guys are typically a force to be reckoned with on the field, definitely within our region and also at Worlds. So Marina, let's talk a little bit about your design process. What kind of goals did you set for yourselves in terms of the design this year?
This year, we really wanted to be capable of doing the most we could for this game. So we all just kind of sat around a table and we talked about what we wanted to do. One of the ideas we used this year is since we have the power cells, we would have one power cell out and pass it around, and that person would give their statement on the idea. And then we would all just kind of talk about it and decide what we thought was best.
All right, so you've got your power cell talking stick, making sure everyone can be heard. What went into those goals? What did you guys think was important?
We thought one of the most important things to be able to do was to pick up anywhere on the field. So our first design was actually a conveyor type system. It was just it was just wide enough to fit one power cell, and they all kind of fit in a line. And our idea was that it could be our intake and our outtake at the same time.
How did you guys decide to set your goals in terms of the control panel, maybe the end game, and everything else that was going on within the match?
We kind of went on an average between what would take the most time and what would score us the most points and ranking points.
Cool. So, what went into those first prototypes?
We decided that we would focus mostly on being able to pick up anywhere off the field and shoot from certain distances. So we worked a lot on our intake and outtake, and the design we came up with was a conveyor-like system. Our conveyor design, we all talked about it and we decided that this would probably be our best option to go with at the moment. So we tried it and we discovered a couple of problems with it. So we had to rearrange our design. So we would use 2 different wheels to intake it, and it would all kind of work up the conveyor, and it would hold them there as we drove around the field picking up more or shooting from a different distance. Now, one of the great things about this was that we almost had 360 degrees of rotation with this, and it's more compact, so we could easily fit under the control panel. Now, we discovered a couple of problems with this design, which were that the balls would jam up on the belts due to having different textures and gripping. So they would jam up and that would cause them to fall out of the side of it. So we all talked about it and we decided that this was maybe not our best route to go and tried a couple of different versions of it.
That's really cool. So you guys found some really strong design characteristics that you liked with your initial prototype, but it sounds like you also ran into some challenges, which sounds like is sort of the theme with this game piece this year. It's a very challenging piece to to utilize efficiently, which is probably part of the game design. So kudos to them. So Marino, what ended up happening? What was the next step in terms of your design, or maybe your next design?
We decided that we would try a V-belt system. So this one was some Lexan in the shape of a V, and we decided that this could be our intake and outtake again. At the opening of the V-belt, we had two skate wheels that would actually intake them and outtake them, and they were staggered at different heights to help give it a more grip and be able to jam less. So one of the great things about this was that we could tip it at a certain height to get the correct amount of motion we wanted for it. And what also is great about this is that we could have a turret with it, but unfortunately with the Neo motors we used, we could not be able to have the turret in the correct position because the motor would stop the turret from spinning, and that defeats the purpose of it.
I feel like iteration is such a crucial part of the build season. Where did you guys end up with your intake for the ball?
When building our robot this year, we wanted to be as fast as possible. Therefore, when designing our intake, we made it as wide as we could. Our team was also unable to get any Mecanum wheels, but they would have just had time to intake in balls, as they would have had to scroll across the front before intaking into our ball categorizer. Our intake consisted of 3 large diameter PVC rollers and a single small hex shaft, powered by a Neo 550 with a 7-to-1 gear ratio. Our design actually started with 4 larger diameter rollers, but we kept losing power cells from them being thrown out. We discovered by accident that if we have a smaller diameter roller, it spins at a slower rate. So that balls are entering the hopper, they are slowed down enough not to be thrown out. Another issue we had was when our robot was intaking too far on either side of our intake, power cells would get chewed up by our chains and then tossed out of the intake. We easily solved this with angle chunks of foam on either side of our intake to funnel them into the center. We also use our intake to climb. Our intake pivots as an arm vertically using 2 gas struts to force it up and 2 redline motors and a 53-1 ratio in order to winch it down and a ratchet slice to hold it during teleop. An extension off the intake mechanically extends as our intake rises using a system of pulleys and dynamocord. We are still working on the actuation of the hook at the end of the extension, but will likely be a mechanical linkage.
Nice. So it sounds like you guys have a pretty interesting intake design. I'm curious, what do you guys do once the balls are on board, right? So you have the balls on the drive base, and they need to be organized and transferred to the right places so that you can prepare to score them. So maybe you can walk through the hopper and maybe some of the roller systems you guys came up with this year.
So our robot is unique in that we use a hopper to handle balls, opposed to what we've seen some other teams do with rotary magazines. We chose to use a hopper after some of our previous designs didn't work out, and we wanted a simpler design that we could quickly mock up with limited time. After power cells are moved into the hopper, we use more PVC hot dog rollers with belts running off another Neo 550, a 5-to-1 ratio, to feed them into our shooter. Our hopper also tips our shooter, so we are able to shoot at more optimal angle and shoot at farther distances. Another cool thing that makes our robot stand out is that we can quickly disconnect the 2 pneumatic cylinders on either side of the hopper in order to fully tip over the top of the robot and gain access to our drivetrain and electronics board. And we can take out another 4 Clecos and remove the entirety of our electronics board.
That's really cool. I like the focus on being able to service things easily and quickly. I think that's sort of one of those things that you could either go all season without thinking about how you're going to open up the robot and work on it, or you really sort of plan for it ahead of time. And it seems like you guys nailed it there. All right, so we've picked up a ball. We have it contained in this hopper, and now we're at the goal. So let's talk about the shooter for the power cells.
Our shooter uses 5 Coulson wheels geared up with an Andy Mark flybox, 1 to 2.5 ratio. We use 2 pneumatic cylinders in order to get 2 shooter positions and vary the RPM of the shooter wheel to fine tune our shot. Our robot does not utilize flywheels as the Coulson wheels provide enough momentum, and with the PID, our shooter easily stays up to speed. Our shooter is also wide, so we're able to actually shoot multiple balls at once, speeding up our cycle times. We use 2.1-inch compression ratio scaled off our 2016 robot.
Nice. Yeah, I love this is probably my favorite part about your robot this year is the shooter that has the wide the wide shooter is so cool, right? Being able to shoot more than one ball at once is such a cool I think unique feature, and is probably going to prove to be really valuable when it comes to quick cycles, which is what this game is all about. So, David, let's talk about how you're moving around on the field. Give us some reviews of your drivetrain.
This year, we machined our own transmissions on our team CNC. Our drivetrain uses 6 Neo drive with a pneumatic shifting 2-speed, approximately 6.5 feet per second and 13.5 feet per second. This year, we also moved our chains inside our robot's frames, saving space and providing them both protection from other robots and stray power cells. We have 4 6-inch pneumatic wheels in the front of our robot and 2 6-inch Omni wheels in the back for quick turning.
So, of course, a robot is one whole complete mechanical and electrical package, but it's nothing without code. So let's talk about that component of the robot as well, David.
This is only our team's second year using Java. Previously, our team used to use LabVIEW, but we moved to Java in order to more quickly prototype and integrate our code. We use a limelight to align our target automatically, similar to other robots, and we're able to pull distance data off the limelight and convert it to get the speed we need to set our shooter wheels at in order to get the optimal shot. We use a limelight to align to our target automatically and are able to pull distance data, which we are able to convert to get speed we need to set our shooter wheels at and calculate the state of our hopper, if we should tip it or not. For autonomous, we use an analog device's IMU as a gyro and 2 internal encoders on the Neozyme drivetrain. Our robot uses 2 limit switches to test the state of the intake, whether it's up or down. We do this automatically, so at the beginning of the match, our intake automatically drops and we can go straight into intaking balls and autonomous.
All right, Brittany, so do you have anything else about the team that you might want to tell the First Mid-Atlantic community?
We'd like to thank our sponsors, Robotics Booster Club, Guyette Communications, Procter & Gamble, Genex Corporation, Greenman Peterson, Inc., Same Page, Printed 3D, Mechanic High School, and Fastenal.
Well, Team 222, Tigertrons, we've got Marina, Brittany, and David, as well as mentor Cliff tonight. Thank you so much for joining us on FMA Plus. If I want to learn more about the Tigertrons, where can I find you?
Go to tigertrons.net.
Awesome. That is where we'll be.
Thank you so much to Tigertron's Team 222 for showing us your stripes, your team, and your robot.
First Mid-Atlantic is grateful to the generous support of our sponsors. We are incredibly fortunate to have one of our strategic sponsors, Picatinny Arsenal STEM, providing a timely message for the 2020 season. Here is Shah Dabiri, Picatinny STEM Manager.
Can't breathe in this thing. Hi, everybody. This is Shah Dabiri. Sharam for the adults, Shah for the kids. If you don't know me, I am the manager of the Picatinny Student Outreach Office. And on behalf of the Department of Defense, Picatinny Arsenal, CCDC AC, and the Picatinny STEM Outreach Office, we'd like to reach out and say hello. It's week 4 of quarantine. I hope you're all doing well, and I hope you and your family are healthy. It's been an amazing year. You all worked hard. Just to let you know, we keep track of these things. How do we do that? We, the Picatinny Arsenal, sponsor 100 FIRST robotics teams, 50 FRC teams, 25 FTC teams, and 25 FLL teams. And each of our teams gets a big kid like me to be a mentor to you. And on behalf of all of us who mentored you, thank you. This year was amazing. It started off awesome with Star Wars and ended a little bit strange, maybe a little too soon. So, this is a learning experience for all of us. Week 4, week 5, we're at home. This is a wonderful way to understand how life can actually be, and a great first learning experience. You've all had a chance to make amazing robots, and things look great until one little thing goes wrong. One little wire is wrong, one little wire is mislabeled, one tire is put on backwards, or one motor is put on a little sideways, and the whole robot stops working. That's what happened this year. Everything was going great. One little virus comes up and, well, we're now all in a holding pattern, back into pits, putting things together. So, my message to you, all you amazing kids, is this. We believe in you, and we're not going to stop believing in you. We, the Department of Defense, are in this for the long haul. We are going to support you this year, next year, and for many years to come. We'll support our teams, we'll support our events, and we'll support our champions, our rookies, and other. Here's why we do it. We're all impressed by you. So, things went a little strange this year, but that's okay. There's always next year. Please take this time to reconnect with friends and family you may have lost over the year, be it digitally, and contact them and say hello. Let them know what you've done. Let them know how amazing you are. And we look forward to seeing you next year. Now, if you don't mind, I'm gonna go see what's outside. Till 2021!
Thank you, of course, to Picatinny STEM for your support of FIRST and FIRST Mid-Atlantic. Up next, we've got Team 708, Hatters Robotics from Horsham, Pennsylvania.
All right, so we're here with Team 708 Hatters Robotics out of Horsham, Pennsylvania. I'm here with Connor, Julia, Michelle, Vinny, Lars, and their mentors, Brian and Tim.
So I heard something about a swerve drive this year, and I also heard, Julia, that you guys decided to try something completely new. Is that the same thing? Are we talking about swerve drive here?
Yeah, so to go along with our strategy this year, we decided to go with a swerve drivetrain. Swerve was definitely a risk for us considering the cost and how complex it was, and especially on the software end. And we have never attempted a swerve drive during the competition season, so it was very difficult for a lot of us.
How are you guys able to get the software to work for you this year? I know software can be a challenge for a lot of teams, especially trying new systems.
Yeah, so it was a very interactive process that involved a lot of code review, time, and testing. It required a lot of we had many discussions, getting the swerve to work for software was one of the main reasons why it was debated for such a long time. And considering that we would buy the modules, since we're so used to making these parts custom, we weren't really used to buying them.
Yeah, that could be a different, definitely a different component of how you manage a season and a build. So Swerve can be contentious, both in the FIRST community and on individual teams. Was everybody on board with doing Swerve?
No, not everyone was on board, especially since it was such a big jump, since we did work on it during the off season, but it takes a lot of development over time with the software, not just several months. It is something that needs to be thought out for several years, and mechanically too, it's so complex with all the different kind of math and working together with the different components. It's just that needs to work together.
So you guys have a really interesting looking robot here. I see this large arm with multiple mechanisms on it. Looks like there's a lot of utility there. What was the reasoning behind that kind of approach?
Yeah, so in the beginning of the season, during our strategy talks and during our what we want the robot to look like talks, we kind of used what we wanted our robot to accomplish to form a basic idea of what we wanted the robot to look like. And part of that was prototyping subsystems independently until we got a general sense of their space requirements and how much space they need to take up. And then once we kind of knew that information, we were able to put together a general idea of what the robot was going to look like. So because we had decided on swerve drive, we initially wanted 2 intakes, one on each side. However, we knew the hopper and the shooter would need to be centralized and that they'd take up a large amount of space. And that left limited space for the intake. And due to the motors and the limited space, that kind of drove us to the decision to have a large articulating arm around a central hopper and shooter mechanism. And also those space constraints caused us to put 3 mechanisms on that arm: our color wheel mechanism, our climber, as well as our intake. And another problem that this limited space left us with was not much room for electronics. So they were all underneath the robot: the compressor, the battery, and the air tanks. They were all hard to place. So we had to find space for those as well.
Yeah, kind of reminds me of the 67 robot from 2012, like having that utility arm. It's definitely a smart way to use a mechanism to do a lot of different things. Definitely a cool approach. But I imagine, I've not been a part of a robot yet that we got perfect on the first time. So did you guys run into any challenges with the packaging of this robot, or do you feel like it went smoothly right out of the gate?
No, there were definitely some challenges. So I mentioned the electronics. We kind of got done the mechanical aspect of the robot and we realized, wait, there's so much more electronics that have to be put onto this robot and barely any space. So we came up with this idea to put the electronics, a majority of the electronics, underneath the robot attached to the belly pan on the bottom. And that included the PDP, the Robo Rio, various other electronic mechanisms that they would be very close to the ground as well. So that was a big risk for us too. But we had nowhere else to put them, so that was our only option.
Definitely a packaging struggle this year. I feel like with so many mechanisms, you've got to combine some stuff to work together. So, Lars, tell me about the intake and the climber working together.
Yeah, so another thing we had this year is because we did swerve, that used 8 motors of a robot, and then Limelight also took up another spot. So that left us with 7 motors to try and come up with mechanisms that could do everything on the field. So when we were combining things physically, we also had to combine them electrically to reduce the amount of motors. And when there wasn't much space for the intake and we put it on the arm, we knew that because a large intake, because we wanted to be as wide as possible to intake balls, it ended up being really heavy. So we needed to reduce the amount of gearbox and motors that was on the end of this long arm. Otherwise, we'd have trouble articulating that arm that needed to go up to almost vertical. So to do that, we used 1 gearbox and 1 motor to power all 3 systems that were up there. So we decided that we could always have the intake and what we call the dingus, our colorway mechanism, always run, but then use something similar to a power takeoff in the drivetrain to opt to using the climber as well, so that you can either run the intake and the dingus, or you can run all 3 of them.
I feel like with one of the things that kept getting joked about this season was like the final boss of Infinite Recharge is your power distribution slots, and like that's such a clever way of combining it. I like it. That lots of people think of the power takeoff from the drivetrain, but you don't often see that in manipulators. But let's break down a little bit into each of those components. Let's start with the intake. Let's dive into it.
Yeah, so for the intake, we knew that because it was on the end of the long arm, it needed to be as light as possible, but we also wanted it to be as wide as possible. So when prototyping, we found that all 3 things that we tried, which are vector wheels, high traction wheels, and polycarb tubes, all work just as well as each other. But we ended up opting to use polycarb tubes because that was the lightest option for us while providing a large area to pick up balls so that the drivers wouldn't need to spend a lot of time lining up. Another thing we considered when choosing the type of wheels that we use was whether it's important to singulate the balls inside or outside of the robot. And this means whether we should have the intake be organizing the balls or the hopper organize the balls. And because the intake and hopper group were communicating with each other, we knew the hoppers could be more of a free flowing system so that it wouldn't need balls to come in very organized. So that allowed us to come up with an intake that was more free flowing as well.
Nice. So we've talked a little bit about your intake. That's only a third of the functionality in this utility arm on the 708 robot for this year. Maybe you guys could talk a little bit about how you handled the color wheel mechanism.
So because we knew we wanted to do everything on the field and we already had an intake that was being used for multiple mechanisms that was on the end of a long arm that could go up and down pretty much all the way, we knew that we could throw our color wheel mechanism on there and that we could bring the arm to starting configuration, fold something out from the arm that could hit the color wheel and then be able to spin that. Because our color wheel mechanism was folding down from the arm, we aptly named it our dingus because it just flopped down there and slapped the color wheel to start spinning.
So the third component of your sort of, multi-mechanism intake is also your climber. So let's dive into that. I'm when I tried to picture this when we talked about it before, how all that packages together, I could not think of a good way to do it. And obviously you guys did. So let's talk about it.
Yeah, so we knew at the beginning of the season we wanted to be able to reach as high as possible on the Endgame bar so that we could be a very useful teammate. So when we were first looking at the layout of the arm, we knew we needed to get as much starting length as we could. That's why in starting configuration, the arm is angled all the way to the top. And then from there, there's just telescoping tubes that reach out all the way and they're angled up so that when it's fully retracted, the hooks are just above the center of the robot so that we can hang nice and level for us. And then because this was using a power takeoff off the intake gearbox, we knew that we needed to be able to limit the amount of friction that was in the system because we wanted a fast climber. So something we did this year is we custom designed our own bearing blocks that would reduce the friction but remain the rigidity of the system, but also allow us to shorten what we would have for overlap length.
All right, so let's talk a little bit more about your pivot arm, or your arm pivot rather. You said you had challenges with limited motor availability, right? You had a ton of motors allocated to your drive base with your swerve modules. So what's something that you had to do differently than you normally would have, considering, PDP slot availability?
So yeah, we knew that because we had a super long arm with an intake on the end of it, but it only had to reach three positions, the intaking position, the starting configuration, and then climbing. Normally we would do something like this with a motor because it has three positions, but we didn't have enough motors available at this point. So we tried something new with pistons. We custom designed our own pivot plate that required pistons to lift the arms. And then on the plate, there was bearings that rode on the outside that then had pistons that could lock into slots. So that those slots would then hold the arm at certain positions while the pistons were pulling it or pushing it to keep it there.
What kind of obstacles did you come up against with these pivot plates? Super interesting mechanism, but I imagine there were some challenges before you had the final product ready to go.
Yeah, because the angles that we needed were really precise because the intake needed to be at a certain point off the ground, the spinner wheel had to be a certain place. We ended up having to redesign these a bunch of times. And then when we also initially calculated the piston strength and stroke, it wasn't correct. So it wasn't able to lift the arm. So with only a couple weeks left in the season, we had to redesign what kind of pistons we would use, but we were able to just make it work for us.
Very cool. So we talked a lot about sort of the multi-mechanisms, right? But Michelle, let's talk about a little bit more about the power cell handling and dive into your hopper.
So our hopper was a big round washing machine like thing. And what makes it different is that it's free flowing. So instead of indexing each power cell, they can come in all at once through our intake, and then it would kind of sort itself out. And keeping it in motion would help with sorting itself out and getting all the balls in place.
Cool. So we know about the impressive utility arm and all of the functionality that it brings to the table. And we obviously know about the impressive agile swerve drivetrain. We also learned a little bit about the hopper mechanism and how that sorts the balls and transfers them to the shooter. Now what I'm interested in is how you guys are actually scoring points besides climbing, right? So we learned about the climbing too. So Vinny, let's start at the early stages of your shooter development. What was some of your thought process and maybe a little bit of the challenges you went through when prototyping your shooter for this year.
Yeah, so basically our thought process the whole time was we wanted to isolate one variable at a time, because when you isolate multiple at a time, you don't know what worked and what was maybe just a coincidence. So like with our first prototype, we really focused on finding what material we wanted to use for our flywheel, because we wanted to use a flywheel, and what material we wanted for our backplate material. So once we figured out those, we went on to our second version and tried to focus more on getting a constant compression, since we already knew the materials, and working on shot trajectory after we got that. With our third one, we improved our compression and we actually added a feeder at the bottom to help get the balls in there. And then our fourth one had all of that we previously mentioned with the feeder. And then we also added a ball ramp so we could just preload it with a bunch of balls, set the feeder up, and it would just do a rapid fire type thing. Some of our challenges that we faced were in the very early stages, we didn't have a feeder. So we were just putting the balls in by hand. And we realized that that gave us really inconsistent results because you could feed it in with your hand any which way with human error. We also had a lot of vibrations caused by different materials and slightly bent axles that we just reused. We fixed that by using spacers rather than shaft collars. And then we actually added some sandbags to the base of the shooter to help keep it from vibrating on the floor. We also faced the challenge of, since we wanted to do a low robot, it needed to be compact down that way. And since it needed to be on top of our extractor, because we wanted to use the circular hopper, it needed to be compact that way. So we couldn't use these giant flywheels that we saw some teams using that worked great for them. Since we had to keep it compact, we needed actually a pre-accelerator flywheel under the main one to help get the balls up to speed that they needed.
I definitely saw that as a theme across prototyping teams of shooters, is that they would try these shooters and it would either be shaky or they'd be feeding it by hand and you wouldn't get the consistency. So I like that you guys thought about the level of consistency there.
Nice. So, Vinny, what's interesting about this robot too that I'm noticing is you guys have two mechanisms that seem to be similar in their capabilities in terms of shooter alignment, right? So you obviously have your swerve drive mechanism, which has all of its advantages, but most of the time that I've seen teams that have turrets, it's actually maybe an answer to not having the ability to produce a swerve drive mechanism or a swerve drive base. But you guys have both. You have a turret and you have a swerve drivetrain. So what made you guys decide to use a turret this year?
Yeah, so basically we decided swerve drive wasn't enough. We wanted our robot to spin all around every which way and have a turret on top of a swerve drive, so it didn't matter which way our robot was going or facing or any of that really. We wanted to shoot from basically anywhere on the field that we could. And we got that with our 2-position hood and our various RPM along with that turret lining up for the shot each time. It helped to keep the target locked the whole time rather than spending a bunch of time trying to line up, right? Because even if you do have that swerve drive, you have to turn it in the exact position that you want to get the balls in. But we thought if we had a turret that could just keep it locked on the target, we didn't need to spend that time turning our robot to line up.
Sure. Yeah, it's a good point. I think the other thing too to think about is, like you said, if you have a turret, then you're isolating your shot angle away from any impact over defenders, aside from obviously blocking, right? But no matter how a defender twists or turns you guys, you're able to lock onto that goal and make your shots. So definitely sounds like a cool, very ambitious and probably very beneficial decision there for sure. Cool. So tons of functionality on this robot, right? Tons of moving parts, really, really impressive packaging. But I'm really excited to learn a little bit more about the software. So Julia, how did you guys use the turret and the swerve that you had to your advantage?
Yeah, so our robot is field centric, which uses a gyro to always face the target. So our turret is always able to know where the target is and allows our robot to easily move around the field. The turret constantly faces the goal using vision tracking, the field orientation and position of the turret with respect to the robot. And the targeting system adjusts the shooter by figuring out the distance from the goal and adjusts the flywheel to match. So this works with automatic maneuverability of the turret, which makes targeting fully autonomous. So no driver or operator input is used. It just does its thing.
I certainly appreciate the deep dive into the robot, but is there anything else about this awesome robot you want to share with us tonight?
Yeah, so it's already been mentioned a little bit before, but it's a big thing for us. So everything on our whole robot, besides the swerve drive modules, were completely custom manufactured and fabricated in-house. And we believe that that's a really important part of the whole experience of robotics, and it's a pretty valuable opportunity for all.
Yeah, that's a cool perspective, right? I think if you have the resources and you can manage the time and you have the technical support, it's definitely beneficial.
So, with obviously our season taking a turn and we've all got to stay home and be safe, how has your team been dealing with it? Are you still working through everything online, or how does that work for you guys?
Yeah, so we connect with each other for various meetings like CAD workshops, software meetings, as well as uh, working on team documentation and the team website. And we do that through a various number of applications. We use numerous professional cloud-based services to enable collaboration, like Autodesk Vault for Inventor and CAD. We use Microsoft Teams for communication, and we use SharePoint for documents and media, where we have almost 1.5 terabytes of media stored. And we also use Adobe Creative Cloud for graphic design.
Sure. So definitely staying digitally connected, even though we all need to be home. That's really awesome. So if you're at home missing robotics, you can figure out a way to get some stuff done as a team as well.
All right, well, that's going to do it for our segment tonight with Team 708 Hatters Robotics. Very impressive robot. I think Libby will agree. Really appreciate a lot of the approaches they took to this year's game. One last question we have for you guys is, if we want to learn more about Team 708, where can we go to do that?
Thank you. So where you can learn more is on team708.org. We have all of our socials on there and a bunch of information about our events and our team.
Well, thank you guys so much. I love learning about Team's robots and fabrication process. Of course, a tip of the hat, pun intended, to Team 708.
Our evenings are getting later, but it's clearly midnight right now. Final team of the evening in our lineup is Team 1923, the Midnight Inventors. All right, here we are with Team 1923, the Midnight Inventors, one of the more prominent teams in the Central Jersey area. I have Parth, Adil, Rashad, Arnav, and mentor Sarith. So with that, Arnav, looks like you're first up to run us through your team at an overview level.
Yeah, so we're a Team 1923 based out of West Windsor Plains Row in New Jersey. We have 118 members divided into 4 technical sub-teams and 2 non-technical sub-teams. So this is our 15th anniversary season. Our team started with just a few people in someone's garage in the fall of 2005. And since then, our team has grown tremendously. We've evolved in terms of how many people we have on our team, the types of resources, the quality of the robots we're able to build, as long with the quality of our outreach and our business, and just in terms of how we can integrate with our community to really make the best robot we can and push the ideals of FIRST at the same time.
What an awesome thing to be celebrating this year. Quite a monumental 15th season for many reasons, but can't wait to see what you guys put together. So let's talk about the beginning of your build season, right? We start sort of with a game breakdown. What does that process look like for Team 1923?
So at kickoff, when we try to determine how we want to play the game, we like to think of a robot in terms of a cloud of mist that doesn't necessarily have any particular functions, but more or less is just something that can do specific tasks in the field, but not in a way that we necessarily know of yet.
So Adil, before you guys could roll up your sleeves and get your hands dirty with the design process, I assume there was some sort of prototyping procedures that you guys went through. Maybe you could talk about that.
So as soon as we had a priority list going, we had to make sure that we tested the designs that we thought of. We had to come up with different mechanisms that we thought would best accomplish the task given to us. So each week we would set deadlines for ourselves to make sure that we were not only on task, but we were coming up with the final design fairly quickly. So what we decided on was instead of a voting system to decide when we're in between two designs, we would weigh the pros and cons and see which one would most effectively align with our priority list in order to accomplish the game task. We also looked at many, many different robots from past years in order to draw inspiration and help us build the best robot possible. So some of the robots we looked at were 2056 from 2016 for ideas on our climber. And for our indexer, we looked from 341 from 2012 to help index the balls, and 973 from 2017. And on our intake, we also looked at 2056 from 2012. And immediately on our shooter, we looked at 254 from 2016 as they built one of the best shooters that year. So we used our resources effectively in prioritizing which parts we wanted to test and just getting proof of concept for different parts. And that was able to be done with our variety of tools and facilities that we have available to us. So we would use our laser cutter to help us get certain parts in a 24-hour turnaround time to help us test as many prototypes as possible.
Yeah, rapid prototyping can certainly help with a streamlined process of deciding what to do. So you went through your design process, you went through your prototyping, and you landed on a robot. So let's, I guess, start from the ground up, Adil, and talk about your drivetrain for this year.
Okay, so our drivetrain for this year was an 8-wheel West Coast drive. And what we did was we analyzed our robot from last year and we saw what could we fix and what could we change in order to make it better. And one of the unique things about this West Coast drive is we included the chain on the outside of the frame of the drivetrain in order for easier serviceability. This also helped us maximize the space that we were using on our drivetrain in order to help it run smoother and allow more space for electronics and other parts on the robot. The robot drivetrain is run with 3 Falcons on both sides, and we designed a custom gearbox in order to maximize the space that we were using. And it's very low profile to help us also include more space on the robot for other mechanisms.
Nice. Yeah, I think serviceability is one of those details when it comes to robot design and FRC that a lot of teams tend to overlook until it's too late. So that makes a lot of sense. I appreciate that level of improvement.
We build our robots with a 6-minute mentality to help fix every mechanism in under 6 minutes, because in the heat of competition during playoffs, it's important to be able to fix your robot in that time, as that is the timeout period you do have in between matches.
Makes sense. Yeah. That's probably where a lot of the elimination rounds are going to be won and lost too, is in that servicing and serviceability. So that's awesome. So Rashad, let's move on to another mechanism within your robot. Let's talk about how you were planning to manipulate the control panel, or as some like to call it, the color wheel.
The first mechanism on our robot is the control panel mechanism. And during kickoff, while determining our priority list, we concluded that the control panel was a lower priority for our robot since the other parts of the game were higher value targets. But nevertheless, we designed a control panel mech in case we chose to use it. So the entire mechanism was 3D printed and is powered by a Neo 550, which contributes to its light weight. It's activated with a rotary piston, which runs off pneumatics, which avoids the need for another complicated mechanism. And its 10-to-1 gearbox and 3-inch compliant wheel allow the control panel to spin at almost exactly 60 RPM, which is the fastest that it can legally spin.
Very nice. So you guys designed for the control panel and then sort of thought that it would come up later, but one of the things clearly that you did focus on was being able to manipulate those power cells. So Otto, let's start with the ball intake.
So our ball intake was primarily designed on the advantage of being able to reach under the trench. This process took a lot of iteration because we found a bunch of dead spots in our intake when we were retrieving the balls, and we had to do some pattern manipulating in order to find out how it will work. And some other iterations included poly belt versus poly cord, and we tried all of these different things in order to find the design that worked best for us.
I think you guys had some lofty goals there in terms of what you wanted to accomplish with your intake mechanism, but based on everything we're seeing, it looks like you were able to hit your marks, which is cool. So now, if I'm not mistaken, you guys had a handful of mentors that were part of a 3-day build, an RI3D or a whatever, 3-day build earlier on in the season, right after kickoff. And I remember one of the things that was realized really quickly was that indexing the power cells into a usable formation so that you could shoot them was probably one of the biggest challenges, right? So it's not so much getting them off the ground onto your robot, but maybe putting them into a single file or whatever formation you need in order to shoot. So Otto, how did you guys tackle that? How do you index the power cells once they're on board?
So with the knowledge that Eric and Sarah brought back from the robot in 3 days, we were able to eliminate some of the prototypes that we were planning on starting with. And we started with a ball tower and a singulator method where 2 runs of polycord will run in opposite directions in order to filter the balls one by one up into the tower. And then we also compare that to a spindexer, which is more of a hopper method, in order to filter the balls one by one into the shooter like that. And our singulator method was also inspired by 341 in 2012, as they used this method to filter their balls. And we saw it work very, very well with the power cells. So this is what we decided to run with, given the resources that we have and how accurately it fit our priority list. And after that, we had to do many iterations on whether we would use polycord or poly belt to run across the ball tower itself. We purchased factory made polycord runs for some spots and 3D printed crowned rollers for the poly belt to help idle the balls and to help make the whole ball tower run a lot more smooth. Whole ball tower is actually run on 2 Neo 550 motors, which really helped us save motor slots, as Rashad will talk about later. Each side is powered through a one-way bearing, which allows rollers to run freely in one direction and idle in the other direction to help filter balls one by one up and through the tower. We found out that if you run both polycord runs in the same direction, it allows the balls to be filtered a lot easier after one goes down. And Parth will talk about the sensor integration that helped us accomplish this. And in total, there are 2 gearboxes that run the whole system, one for the singulator and one for the ball tower itself.
It sounds like a lot for mechanisms that just pass the ball from the intake to the shooter, but it seems like an infinite recharge. That's actually one of the harder components of being able to shoot a goal, is to get the ball from spot to spot inside the robot. So clearly you guys spent a lot of time on that. But now we've, indexed and singulated all the balls in a nice little line here. And let's talk about the shot. What kind of mechanism work did you do for the ball shooter?
So this year we used a flywheel shooter with a West Coast Product 60 durometer wheel. And this shooter is run by 3 Falcons for shot power. And we can even shoot from behind the control panel, which is something that helps us run shorter cycles. Another thing that we had to iterate on with the flywheel shooter was we had to change the compression a bunch of times to make sure that we found what worked for us and iterated in a way that would allow our shots to go in every single time we attempted them. Another thing that we had to look into was how are we going to save the maximum weight on this mechanism, because weight was an issue for us this year, and we were able to solve that by making the entire flywheel shooter completely out of Delrin, which was really helpful in saving weight. Another thing that we had to put on in order to get the caterpillar of shots that we wanted to make them go very fast was we custom milled inertia wheels to maintain the wheel RPM in order to release the balls efficiently and quickly into the high goal. Another thing that we decided to incorporate into our shooter was a turret, and we custom laser cut a 122 sprocket made out of Delrin that we used inside of a bearing sandwich on quarter-inch aluminum plate in order to constrain the turret and allow it to run smooth. And in order to come up with this design, we had to iterate on it about 7 or 8 times to find the bearings that fit the right turret pattern and allowed us to move fluently. And so the whole turret is run off of a Neo 550 and geared to spin 540 degrees in under 1.5 seconds in order to minimize target acquisition time.
So this thing is locking on right away and it's ready to shoot as soon as you guys want it to. That's very cool. So Otto, we've learned about the power cell manipulation, how you guys are scoring throughout most of teleoperated period. How did 1923 handle the Endgame this year?
We drew inspiration from 2056's 2016 climber. We were able to build a telescoping arm this year, and it allowed us to climb on uneven bars. One of my favorite experiences from the season was when we first tested our climber. We tested the constant force springs and the 3D printed mounts that Sarah, our mentor, brought us. And we tried it for the first time to see how quickly it would engage, and we almost put a hole in the ceiling of our lab, which was an experience. It was very scary. We did not expect it to go that quickly, but it did anyways. Our climber gearboxes this year were made of Delrin in order to minimize weight. And like I said, we had 30 3D printed concept four spring mounts and a ratchet brake operated by a rotary pneumatic in order to engage our brakes to hold us up.
What a cool comprehensive look at the mechanical systems. So Rashad, you're the guy to talk to about electrical systems. Let's walk through that on the robot.
The defining feature of our electrical design has to be our upside down E-board. Due to all of the mechanisms we wanted on the robot this year, we opted to put the belly pan on top of the dry base, which gives space under the robot for the electrical components. This E-board, although initially thought of as an inconvenience, worked for our benefit, since the robot could be easily flipped onto its shooter tower and be serviced by both the electrical and mechanical subteams at the same time. And another important part of Singularity is redundancy. So firstly, we chose to solder as many connections as we could, since that was the most solid connection that we could create. And last year, the electronics for our robot were subpar. CAN repeatedly dropped out, and we frequently lost comms during matches. And we wanted to address this problem this year. And luckily, a friendly neighborhood team called Flight Crew already had a solution. So we adapted their design for our specific workflow, and the result was a centralized CAN system, which functions similarly to how a PDP works. We even nicknamed the system CDP, or CAN Distribution Panel. So further, each component on the robot had 4 wires going to it, 2 green and 2 yellow, ensuring that each component always receives a signal. And this decentralized approach also allows for individual components to die without affecting the overall CAN loop. And one problem that we faced this year was a lack of PDP slots. We opted for fewer pneumatic components and more motors, since this saves on weight. And as a result, we had 15 motors on the robot. And the PDP actually has 16 slots overall, and we can't integrate motors together unless we use bag motors, which we chose not to do. But this was a problem, since the conveyor and indexing systems we designed would work best with motors for each individual poly run. However, we integrated segments of the system to run off single motors. Specifically, in the intake, we had to run both the top and bottom polybelt runs with a single motor. So we used one Neo 550 on the top roller, twisted a strand of polybelt 180 degrees to reach the bottom roller. And with this, both polybelt runs could run in opposite directions and intake balls properly off of one motor. And as Adil touched on earlier, our turret has a full range of motion. And to accomplish this, we placed all of the Falcon 500 motor and CAN wires into one cable sleeve attached with a stack of Andersons at the top and bottom. This worked extremely well because it makes the wires extremely replaceable, since we also created backups of this specific cable run. So overall, our electrical subsystem this year is our most robust ever.
What I know about FRC is that you could have one of the most well-machined, well-built turrets or shooters or intakes on your robot, but it's really not worth anything unless you have the software to operate it efficiently. So Parth, I've been told you're the guy to talk to about software and about programming. So maybe you can give us a high-level walkthrough of some of the automation and some of the software that makes Singularity so awesome.
Our first major automation was in automating the entire ball path, from the intake to the turret. When we press a single button, that we can enable our automatic indexing, which the purpose of is to automatically get all 5 balls into the ball tower. Enabling it will cause the intake and indexer to periodically cycle until a proximity sensor detects a ball right over the center of the indexer. From here, it will automatically push the ball inside until it reaches a second proximity sensor. These proximity sensors were spaced so that the balls are correctly spaced and we can fit all 5 inside of the tower. This automatic indexing system can count the number of balls that enter the robot, so once all 5 are in, it will automatically turn off and get ready to shoot. That brings us to our second major piece of automation, which was our turret and shooting mechanism. Our primary method of detecting the target was using a limelight. We used a limelight because it was really easy to set up, and it's also really easy to calibrate if we need to do so at different competitions. We also liked it because it was easy to set up multiple pipelines that can be switched to at runtime, which we use to allow the limelight to detect the target at multiple distances. With the angle and the distance to the target estimated by the limelight, we could use a PID loop on the turret to track the target. We were also able to add a calculation to compensate for movement of the robot. What this means is that even if the robot is driving or spinning, the turret will be on the target and not lag behind, which allows us to shoot balls while on the move. When the shooter is starting to rev up and you're preparing to fire, the turret will automatically move from its home to where it last saw the target. We used a gyroscope to allow us to remember where the target was, even if we moved. And if it can't find it, it will scan for it and find it. Finally, based off the distance from the limelight, we can automatically calculate the appropriate RPM to rev up the shooter to in order to get an accurate shot. We use PID on the shooter as well to ensure that the balls are at a constant velocity, even if we shoot multiple of them in a very rapid succession.
All right. Well, it sounds like the clock has struck midnight, and that's all we have for tonight with the Midnight Inventors Team 1923. Thank you guys so much for taking the time to speak with us tonight. If we want to learn more about your team, your organization, or Singularity, where can we find out more?
Thanks. You can find us on Twitter at FRC1923 or on Instagram at Midnight Inventors. You can also find us at facebook.com/FRC1923 and on YouTube. Our channel name is The Midnight Inventors, and we'll be dropping our reveal video for our robot after tonight's show. So feel free to stick around if you want to see that.
All right. Well, the clock is tolling on the witching hour for Team 1923. Thank you so much to the Midnight Inventors for such an awesome segment.
Thank you so much to all 4 of our teams tonight for your time on FMA Plus. Please make sure to stay tuned for our live post show. And don't forget that next week, First Mid-Atlantic is going to be kicking off the show with their official awards ceremony right here on the same channel. So we will see you next week, and we'll see you next for live post show. All right, everyone, we are here and back for our live post show with Team 708.
Yeah, with that tonight, we have Lars and Connor and their mentor, Brian, from 708 Hatters Robotics. We heard a little bit about their team and about their robot from them earlier in this segment. So we're going to jump into some questions with Lars and Connor. Remember to keep posting your questions in the chat, as we'll be picking out as much as possible to present to these guys during our Q&A session. So with that, Libby, I'll go ahead and throw the first question at him. So the first question from the chat, first off, they wanted to say, hey, 708, good to see you. What is one of the things that sets you apart from other teams?
So for this year, what really set us apart is the amount of custom designing and manufacturing we did. So everything on the robot, except for the swerve drive, was all custom and made in-house. So like the turret plate that we made out of Delrin was made on our CNC. The bearing blocks we made on the mill, one of those took 4 hours to make. And this would not have been possible without the help of our school and our sponsors. Our sponsors this year are Vulcan Spring, HH, the Happel Horsham Educational Foundation, and Lockheed Martin. What we did this year would not have been possible without them. And then also something special we did this year was our swerve drive end turret allowed us to be extremely maneuverable while staying locked onto the target so we could turn and shoot at the same time, which made us really hard to defend.
Yeah. One of the questions we were going to ask you next was how long did you spend building the arm and the bearing blocks? But thank you for being ahead of the curve here. So one of the other questions we have for you is you guys seem to love multi-purpose telescoping arms for climbing from 2016 to 2018 and now 2020. I guess you like even numbered years for those as well. Any reason you have such a strong preference for multi-purpose arms?
Well,
Just because they're, Connor, you can take it.
So one of the main inspirations for our arm this year was drawing from our 2016 robot. And we decided that with all the stuff we wanted to accomplish, that this packaging would be the most efficient for the design that we were going to go ahead with. Hence why we have 3 mechanisms geared off of 1 gearbox, all on the same arm.
Nice.
Another reason we like to do that is because when you have such a long arm like that, it's going to be a bunch of aluminum. So you might as well use the extra weight to turn it into multiple mechanisms to save weight overall, because if you're going to be building something that large, might as well add something small onto it so you don't have to do something else for that.
Yeah, that makes sense. Cool. So next question. Swerve drives have become increasingly popular in the Mid-Atlantic region over the last few years, especially. Were there any other teams that you guys drew inspiration from in deciding to switch to Swerve drive for this year?
There wasn't any teams in particular. I mean, we've seen lots of teams in the area, like Cybersonics. We talked to them about how they were able to do it because they did something similar, and we drew a lot of inspiration from them.
I feel like the sense of community in First Mid-Atlantic is awesome, from like excitement on Discord to just being able to help each other with things like Swerve Drive. Question from YouTube chat on the topic of the Swerve Drive. Did you guys have any difficulties initially with having a Swerve and a turret, right? So, you know, there's usually the philosophy of you only need one or the other. Did you guys ever have issues with those two sort of like over aligning or being too hard to manage at once?
Well, because this was our first year doing a Swerve Drive and we only got it up and running just before the build season started, we did have issues initially with just the Swerve at first before the turret came into play. So we kind of got those sorted out. And when we introduced the turret, there was a lot of tuning that needed to happen to ensure that when we're moving, spinning around, that the turret is staying locked on. The vision targeting had to be worked out because we've never done any vision targeting or anything like that on a robot that is so maneuverable like this one was.
Cool. Yeah, I mean, I feel like it's one of those things where everything needs tuning, and trying a ton of new stuff at the same time can definitely be hard. So mad props for adding the Swerve Drive in. I know it's something that my team's definitely touched on and then been a little too afraid of. As far as the robot weight limit, you touched on that earlier. We're making sure you got your multi-purpose arm, making sure you're accommodating for weight. How did you guys do when it comes to the weight limit? There's a lot of functionality on the robot, so I'd love to hear sort of the journey of what the robot weight struggle might have been.
It was quite a struggle to say the least. We ended up finishing the robot for a good amount, and then ended up being at 138 pounds. So we spent the next couple of weeks trying to drop those 13 pounds. We did that by lightening pretty much all the climber. We dropped a gearbox off of the intake and climber. We normally had one on each side. So we dropped one of those, and then we lightened it by doing more aggressive lightning patterns on pretty much every plate on the robot. And then that ended up being pretty much all the weight right there. But another issue for us with doing that is the robot ended up coming out later. So we really finished the robot like the Wednesday before Hapro. So the drive team and software really had very limited time with the robot because we had to spend so much time taking stuff off.
Oh yeah, it's the classic beat the clock aspect of build season, right? Even without the bag or the crate or the stop build, you're still pushing to the very end, right? So I'll be the one to tell everybody this. The final segment didn't include aspects about this next question, but 708 did talk about it in our recording session. So I think this might be a good place to share. The question is, how did you guys come up with the strategy you wanted to pursue?
So at the very beginning of the build season, on kickoff day, that weekend around there, we all sat down as a team. And first we read through the whole manual as a team to learn the rules. And then we began talking about ways to score in the game and how we wanted our robot specifically to play the game. From there, we took our idea of how we wanted to play the game and began thinking about, well, what do we want our robot to look like? What is the robot going to need to accomplish? And then there were a few important decisions we also had to make, such as what type of drivetrain are we going to use, and do we want a tall robot or a robot that can fit under the trench run?
And I think the decisions you made and the robot you came up with, first of all, are super clean, but also was a very ambitious robot. And obviously, you guys got to compete in week 1. On top of that, you guys hosted the week 1 event. So I'm always curious with teams that both compete and host. What challenges are unique to your season, given that you kind of have to handle all of that so early in the season and in the year?
We don't really see it as a challenge. We see it more of as an opportunity, because hosting allows us to spread what we do as a team, and it also gives us the extra opportunity to host it, because that's something else that's logistics. It's the volunteering side of it, and be able to see all the teams come into our school and see what we do is really fun. Because something that I did was out in the pit when I was in the pits this year, teams would come in and see our shop and be like, wow, this is awesome. So hosting's a really fun experience for us, because then we can show teams what we do, and then we can share with them the things we do so that they can learn from us.
Okay. Next question. This one's a little bit more fun, I think, less technical. Have you guys decided on a name for this robot?
I don't think we have, actually.
Okay. Well, since there's only 2 of you,
oh no,
Lars, we'll start with you. What's your best shot at naming this awesome machine?
One of the things we thought of was naming it similar to an anti-aircraft cannon, because the arms sort of look similar to something like that. So one of those could be a good option for us.
Okay. And Connor, your thoughts?
I would have to say maybe Pegasus, because last year the unofficial name for our robot was kind of the unicorn, and I believe this year it is upgraded to Pegasus.
All right, keeping it mythical. I like it. Very cool. I feel like robot names one of those things that either come super down to the wire or like teams have planned out aggressively, and I love the sort of like, oh yeah, sometimes they just happen.
Yeah, like you're just standing around the robot and somebody screams something, and then there's like this unanimous like, that's the name of our robot.
That's it. Exactly. So this is a question we like to ask sort of all teams. I think we missed it last week, so we were in sort of a bunch of different things. But in terms of build season, every team has this like moment of like, oh, this is it. Or like that big sort of like colliding, everything comes together and clicks. So what was Team 708's aha moment this season?
Well, for me, I thought it was really cool when we finally got to see the gigantic arm in action, and the pivoting, locking into all those different positions. Finally seeing that work, which took so long to get working, seeing that actually be successful was really cool.
I would say there was more than like one aha moment, because there's so many risky things we tried this year. Like seeing it get on the scale, being under 125 pounds, that was amazing, because we were at 138. So it was like, yes, we're gonna be able to compete. And then seeing the swerve drive start working, because that was completely up in the air, and not many of us were able to focus on looking at that because we were doing other things. So seeing it drive around was super, super nice. And then the other thing was seeing the turret. There was one point where we saw the turret staying last on target as the swerve drive was driving around, and that was really awesome to see. So it was more of a buildup of small things where all the risks started to pay off.
Yeah, I feel like with a team that's trying new things all at the same time, I think that's got to be a really meaningful aha moment. So congrats. I think it's a clean robot. I always think 708 has some of the cleanest like video and media out there. So I love getting a chance to take a look at it here on FMA Plus. Thank you guys.
Absolutely. All right. Well, Lars, Connor, and mentor Brian, thank you so much for taking the time to talk with us tonight. That's going to do it for our live Q&A session with Team 708 Hatters Robotics. For all of you at home, don't forget to have your lead mentor check their email for information on applying to be on a future episode of FMA Plus.
And of course, a huge thank you to the entire FMA Plus crew for making this happen. We couldn't do it without the whole group that's screening teams, interviewing them, and editing down these team features every week, as well as moderating chat, coordinating social media, and keeping you all informed. So don't forget that next week, right here, same time, same place, First Mid-Atlantic is going to be kicking off the weekend with our awards ceremony. That's going to celebrate our Dean's List finalist, Volunteer of the Year, Woody Flowers Finalist Award, and of course the Chairman's Award for the season, which as we all know have been judged digitally. So once that is complete, Saturday evening, we will move on to our week 4 episode of FMA Plus.
Absolutely. We'll see you next Saturday for those awards and another awesome episode of FMA Plus. Have a great night, everybody.